morning, ladies and gentlemen, and distinguished guests. Thank you for joining us today at the KAST AASSA International Webinar. My name is Yong-Ho Park, Professor of Seoul National University. I'm very happy, and it's my great pleasure to be a moderator today webinar seminar. The Korean Academy of Science and Technology and the Association of Academies and Society of Sciences in Asia jointly held today's webinar under the theme of global climate changes and zoonotic infectious diseases. This webinar will be live streamed on KAST YouTube channel. We hope you will stay with us and enjoy throughout the whole program until the end. This webinar will consist of 2 sessions for 2 days. Today, we'll talk about impact of global warming on our living conditions. Let us begin KAST AASSA International Webinar. Okay, it is my great pleasure to invite Professor Wook-Jun Yu, President of the Korean Academy of Science and Technology, for his opening remarks. Please join us to give him a big hand.
Good morning, Honorable Professor Ahmed Nuri Yurtsiv, Acting President of the Association of Academies and Societies of Sciences in Asia, distinguished guests from home and abroad, ladies and gentlemen. On behalf of the Korean Academy of Science and Technology, it is my great pleasure to welcome all of you to the AASSA KAST Online Regional Workshop, co-hosted by the AASSA. Today, we hold this webinar on global climate change and zoonotic infectious diseases. As everyone knows, the world is facing various global crises, such as climate change, natural disasters, and endemic. We assume that climate change may cause poleward expansion and seasonal changes of some diseases, and also climate change drives zoonotic epidemics by altering host pathogen interactions. So, this webinar reviews predictions of various zoonotic risks based on climate change. During the 2-day webinar, I am very confident that we can take a small but meaningful step by sharing information and experiences. I truly hope this webinar will be very successful and productive. I would like to take this opportunity to express my gratitude to Professor Yong-Ho Park, Chair of the Organizing Committee, Professor Seung-Bok Choi, Director of Secretariat of AASSA, for their contribution and dedication in making this webinar. I also would like to extend my special thanks to the speakers and the executive board members of AASSA. Let me now close by wishing you all a delightful and fruitful webinar. Thank you very much.
Thank you very much, President Yu, for your wonderful opening remarks. Now I'll move to the next welcoming remarks. The Professor Ahmed Nuri Yurtsiv, Acting President of AASSA, the Association of Academy and Society of Science in Asia, for his welcoming remarks. Please join us to give a big hands.
President Yu, dear colleagues, distinguished participants. Good morning to you all. I would like to thank Korean Academy of Science and Technology, KAST, for hosting this webinar on the global climate change and zoonotic infectious diseases. Korean Academy of Science and Technology has been not only the host academy of AASSA Secretariat, but also one of the most active in the AASSA activities from the very beginning. The topic of this webinar, the global climate change and zoonotic infectious diseases, is very important for both scientists and human society. As the recent COVID-19 pandemic has shown, we are increasingly under the influence of zoonotic infectious diseases, and they are disrupting every sector of human life. Had it been under normal circumstances, we could have held this meeting face-to-face, and I would be with you where I always feel myself at home. The spread of zoonotic diseases and infection of human beings depend upon many factors, and global climate change is one of them. Global climate change and other likely causes of the spread of zoonotic diseases are, of course, to some extent natural. Yet, we do know that they also depend upon the interaction of human beings with their environment, especially with the natural habitat of non-human populations. In other words, zoonotic diseases and their spread are not just natural, but also human. It is thus imperative that we, human beings, need to be more and more responsible in our interaction with the nature. By examining the global climate change and zoonotic infectious diseases, this webinar will, I am sure, contribute to not only the analysis of the phenomena, but also to responsible human practice, both in science and society. In concluding my remarks, I would like to congratulate KAST for organizing such a comprehensive webinar and pledge the continuous support of AASSA.
Thank you very much, Acting President of AASSA, as well as Professor Nuri. Now we will commence the session 1. It's my great pleasure to introduce session chair, Dr. Yu Gwang-soo. He is the Senior Research Officer of the Korean Zoonotic Research Institute. Please welcome to join the big applause to the session chair, Dr. Yu Gwang-soo.
Good morning, everyone. Welcome to the first section entitled Climate Change. I'm Gwang-soo Ryu from Jeonbuk National University, Korea. I'll be serving as chair of this section. First of all, I wish to thank KAST and the AASSA committee for this great symposium. Let me introduce the first speaker. The first speaker is Professor Byung-Ju Son from Seoul National University. He has been an international leader in the radiation and climate science area. He is going to speak the topic impact of global warming on our living condition. Would you please start your speaking?
Thank you, Mr. Chair. My name is Byung-Ju Son from Seoul National University, and it is my great pleasure to have this opportunity to say about global warming impact on our living conditions. Let me first say about subtle difference between weather and climate. This matter of time average or any instant feeling about the weather conditions or atmospheric conditions. Weather is everyday feeling, like feeling hot and humid. If we say something like the 35-degree on August 15th in Seoul, then we are talking about the weather. But if we say this summer will be very hot, then we are talking about the climate. So even though the weather and the climate sciences deal with a kind of same target, including humidity and the temperature, rainfall, and clouds, then there is a subtle difference between the time scales. So climate is kind of long-term averages of weather events. In summarizing such a subtle difference, Mark Twain once said, "The climate is what you expect, and the weather is what you get." So summer will be hot, but how hot is kind of weather regime? Today I'm talking, I'll talk about the climate change, kind of long-term average of weather events. The climate, in fact, changes naturally as well as currently anthropogenically. If we say about the past climate, the Earth's age is 4 billion years old. But we have certain evidences that show the climate has been changed quite rapidly over a longer period. For example, over 400,000 years, using the ice coating analysis, temperature has been fluctuating a lot compared to current temperature. So, for example, was 350,000 years ago, the temperature was below 8 degrees compared to today's temperature. And you see temperature rises and goes down again and rises. So the temperature recurs continuously, having minimum and maximum. And the maximum temperature periods are called interglacial period. So if you look at this figure, the temperature has been fluctuating quite large, and the interval seems to be quite large too. Interestingly, the carbon dioxide concentration is consistent with temperature fluctuation over 400,000 year period. If we take a look at the last glacial period, which occurred 12,000 years ago, Northern Europe, including Britain and Scotland, Northern Germany, and Northern Poland, though all Northern Europe was covered with snow and ice, like today's East Greenland, where snow and ice stays over a long period. So whether at that time, about 12,000 years ago in Europe, would be like this, having cold and bitter temperature. If we take a look at more recent centuries, like 1565, there was called the Little Ice Age. There's one painting drawn by Peter Bruegel. The title is Hunters in the Snow. If you take a look at this painting, then there's kind of watermill whose wheel is frozen very steep, and distance there are people skating, and weather seems to be very cold and calm, and the particular day was kind of overcast. So in that nearly 500 years ago, there was very cold. In particular, European weather seems to be very cold than today's weather. Even after 100 years after that period, in 1677, another painting shows that the UK, the London shows Thames River was frozen completely. That title was looking eastward towards the old London Bridge. If you take a look at this painting, there are some people enjoying, like shootings and skating, and the dogs were playing. But these, a couple of centuries of old, little ice age was followed by a kind of warm period. Then currently, the temperature has been rising quite rapidly, mainly due to the carbon dioxide emission caused by fossil fuel consumptions. There are ample evidences showing the temperature has been rising over globally. For example, if there is an increase in temperature, then immediate consequence will be ice melting, because ice melts when temperature rises. Then there were photos taken at the same place showing kind of different time situation. Top two panels are the photos taken at the same spot showing the AASSA Glacial in Argentina. In 1928, there are a lot of glacier covered the glacial area. Then 2004, after 80 years, then these ices turned into kind of nice lake, but all the glacier disappeared. Even in Himalaya, Rombo Glacier shows in 1968 with a lot of glaciers covering this valley area. But 2007, all these ices disappeared and the glacier retreat, implying the temperature has been rising. But this picture vividly shows how temperature has been rising. This picture is the observed temperature. The thermometer measures temperature. So we have certain record starting from early 1800. Then we have the observation record of temperature over 200 years. Here, the blue color means the cold temperature, and red color, on the other hand, indicates kind of warmer temperature. So over 200 time span, you immediately recognize the temperature has been rising from generally the blue color to red color. Amazingly, the hottest 10 years amongst 200 years are in 21st century. For example, the hottest year was 2016. The second hottest year was 2020, and 2019, 17, 15, and 2005. 10 years are all found in 21st century, emphasizing that temperature may be rising quite rapidly in recent years. And this is really public attention brought by New York Times last year, nearly 1 year ago. Huge icebreak separated from Antarctica. The Antarctica is covered with a lot of ice, but this big iceberg, whose area was nearly 2.5 times Jeju Island, whose area is 1849 square kilometers. And this iceberg got separated from the ice shelf, then moved to the weather sea and eventually melted away. In that way, the Antarctica is losing a lot of ice mass. The same can be applied to Arctic sea ice. It will lose even all the entire Arctic sea ice very soon, perhaps after 20 years. So during the summertime of mid-2040s, probably we'll see the empty ice during the Arctic Sea. That's very important consequences of global warming. It was last year when we have very extreme weather. Currently, the heat waves are very important and disastrous weather event. And by the way, heat waves are more frequent, getting more intense, and more persistent. One example was occurred in west coast of United States and the west side of Canadian British Columbia. A lot of wildfires actually, make people endangered in this California and Oregon and Washington area. One time in Canada, British Columbia, Lytton City, it was recorded temperature 49.6 in centigrade. It's not a Fahrenheit. It is centigrade, 50 degrees centigrade in Canada, which cannot be imaginable in the past. So in this kind of heat waves, people got heat exhausted, and they were forced to evacuate into the shelter like this, to the well air conditioned the gymnasium. People stayed there to avoid the heat. So this kind of the climate change induced extreme weather are more frequent, more intense, and more persistent in nowadays. What causes this kind of weather and extreme conditions where people cannot live comfortably? Probably we'll face a more harsh condition in the future. So that goes to carbon dioxide concentration. Here we have like 300 years of carbon dioxide concentration record. There are two sources here. After 1958, the people can really measure the carbon dioxide concentration with the devices. Before that, we have some information obtained from ice coring, because ice can be formed from snow. And when snow falls down on the surface, it captures a kind of air and preserves for long years. Then we can drill the ice and take that air bubble and diagnose what concentration was when the ice was formed. So over nearly 300 years, the carbon dioxide has been quite steady until so-called industrial period. So after global industrialization, then CO2 picks up quite steady increase. then it is in recent years to see kind of rapid increase in carbon dioxide concentration. Then why carbon dioxide is blamed as a culprit of global warming? In order to understand, we have to understand the Earth is maintaining some sort of equilibrium of radiation energy. Here on the right-hand side, there's a blue planet, our planet, Earth. The Earth receives solar radiation energy, so-called solar constant. Then some of energy, about 30%, is reflected to the space due to the clouds and by land. So absorbed solar radiation can heat or warm the Earth. If the Earth warms, then its temperature will give radiation emitted from space, emitted from Earth's surface. This is called Earth-emitted radiation. But between these two radiations, solar radiation and Earth's radiation, they maintained some kind of balance. This is so-called equilibrium of radiation energy. In that way, the Earth can maintain some sort of very stable temperature over long years, although we see the glacial period comes mainly due to astronomical forcing. But if the carbon dioxide increases, there is so-called greenhouse effect. We just saw the energy balance is achieved between solar radiation and emitted Earth radiation. But if we take the atmosphere has a kind of carbon dioxide, greenhouse gases, such as carbon dioxide and methane, water vapor, and ozone. If those greenhouse gases are missing, then atmosphere cannot play anything on changing atmospheric radiation or Earth's emitted radiation. So the solar radiation comes to the surface, and all energy just go outside to the space. But if there is the atmosphere containing greenhouse gases, then atmosphere absorbs infrared radiation, and some will escape to the space. Then there is another extra infrared radiation coming from the atmosphere. This is a so-called greenhouse effect. So when there is increased greenhouse gas, then there will be more incoming infrared radiation from the atmosphere. So with the atmosphere, the Earth can be kind of warm so that people can live comfortably in the Earth. The problem is this part is getting bigger because of carbon dioxide increase. We achieve more in terms of economic development, social activities, and the population growth. Then this part will be larger, giving the surface temperature warmer. So far, we looked at quite a longer period how the climate change occurred naturally, and we're starting to see the global climate change, mainly forced by anthropogenic forcing, the carbon dioxide increase, methane increase, and those things. So CO2 has been rising continuously, recently increased fast, and that gives kind of warm and extreme heat waves, the sea level rise, and ice loss in both poles, and more hurricanes, more extreme rains, And these are giving a lot of people moved from one location to another because of the weather disasters and the associated consequences. And agricultural disturbance is also one important aspect of global the warming and the global change. So we can expect temperature change in the future as well as a precipitation change. So what about the future climate change? So we are more interested in predicting climate in the future because we can prepare how we act against increased greenhouse warming and associated climate change. For the climate change prediction, we rely on the climate model. The climate prediction model is very similar to the weather prediction model. And the climate model has a so-called grid. You see the latitudinally and the longitudinally divided areas. Each rectangle is called a grid. And if we take at one grid vertically, then you see vertically divided layers. So three-dimensionally, we define all various the climate variables like temperature and humidity and wind, cloud. So at each column, there are so-called physical processes, including how rains are formed, how clouds are formed, how the heat exchange actually takes place between atmosphere and ocean. So including all this as a model parameters, then we need kind of how much carbon dioxide in the future. But carbon dioxide is turned into a radiative forcing. I showed you how strong the greenhouse effect toward the surface. So the carbon dioxide concentration should be converted to kind of physical variable, radiative forcing. So we should know about future CO2 concentration. So adding this CO2-induced radiative forcing or radiation energy into the model and integrating this model with time, then we can have the all climate variables in the future. So we need the carbon dioxide concentration in the future to run this model and to get the climate aspect, climate features in the future. So how we obtain the carbon dioxide in the future? We have some kind of tools in which there are three important factors to regulate carbon dioxide concentration. One is P, that's the population growth. Because we deal with kind of the carbon dioxide concentration. So if there are more people, then we'll consume more fossil fuels, then that will increase the carbon dioxide concentration. Then A stands for affluence, how rich the individual is in the future. So that can be expressed with GDP per capita, but in dollar. And the T is greenhouse gas intensity, this technology, how heavily we rely on carbon dioxide concentration in producing or consuming $1 value. So actually the technology can reduce the carbon dioxide consumption, but because of population and the growth in wealth and greenhouse gas, then we can project the total carbon dioxide emission. This is called the scenarios. So we need the scenarios for the future climate change prediction. There are some the pathways from 1960s to 2100. So we are now standing here around the 2020. Then this on the right-hand side, there are future CO2 concentration we may expect given in carbon dioxide emission in gigaton. So there are various ways, okay, if we give any effort on reducing carbon dioxide emission, so-called business as usual, then the emission goes up very high. So this part is in the high emission side. On the other hand, the other side is a low emission side. So if we give a lot of effort on reducing throughout the rest of the 21st century, then carbon dioxide concentration go down substantially, reaching zero emission. Then there is a negative emission by the end of 21st century. So we have various the carbon dioxide emissions throughout the 21st century. Then, as I introduced, these carbon dioxide concentration now is converted into radiative forcing. Then radiative forcing is included in the climate model. Then we have this kind of mean temperature increase in the future. So individual curves are representing the carbon dioxide path. So if we just don't give any effort on reducing, then by the 2100, the temperature goes up like 6 degrees higher than current year. But depending on the path and model spreads are here, but considering all those uncertainties, there is consensus that at the end of the 21st century, temperature will likely rise to between 1.9 to and 5.2 degrees compared to present. So the model prediction indicate that temperature will keep rising into kind of environment in which we really hard to live in. So this is the annual temperature change. There are 3 columns. The first is actually mid-21st century and end of 21st century and end of 22nd century, the 2200. And depending on the scenarios, very low emission scenario and the highest emission scenario, you immediately recognize the temperature will rise very rapidly. For example, if we don't give any effort, temperature will rise to nearly 11 degrees centigrade by the end of 22nd century. If we reduce our scope to kind of 21st century, then temperature rise is here. But if we give a kind of substantial effort on reducing the carbon dioxide emission, temperature still rise quite large, like a 5 to 6 degree in centigrade rise in higher latitude and the polar regions. So this is really kind of very pessimistic views on global climate change. Not just the temperature, but also the changing climate gives a lot of influences on other climate variables, such as precipitation change. Precipitation change is predicted to have more precipitation in the future. So the total rain amount will be increased, but not equally everywhere. It's not well distributed. If you take a look at the kind of dark green area, these areas are actually the large rain falling areas. So there are rain, but these areas are quite dry, Mediterranean Sea and northern Africa. So kind of polarizing features. So the wet area is getting wetter and the dry area is getting drier, polarizing the geographical distribution of rainfall. This will cause a lot of problems as well. Some area will get flooded, some area will suffer from aridity and dry conditions. And one of important consequences of global warming may be sea level change. Sea level can be varied due to the warming trend. So warm temperature will actually give ice and snow melt. So polar region will lose their freshwater storage from snow and ice. So that will give more water level to ocean, open ocean. On the other hand, the ocean itself gets warmer, then there will be the sea volume expansion. So there are two influences on sea level rise. So prediction indicate that by the end of century, 2100, they're nearly 0.8 meter, but depending on the scenario itself. But the sea level change is a long kind of slow processes. Even after we stop the carbon dioxide emission at this point, sea level will keep rising until we have kind of equilibrium condition due to the carbon dioxide cycle. So chunk of a bunch of, a lot of carbon dioxide will go to the ocean, then stay there and emit over the centuries. So we'll expect the sea level rising quite continuously over the centuries. Okay, this may be the summary, how those, the climate changes in the future. We have already ample evidences of showing the global climate is different from the past, mainly global warming. So it can be influenced directly and indirectly on our planet Earth or our living conditions. Some of impact would be direct, like a rising maximum and the minimum temperatures. We have, if we look at day temperature, there is maximum temperature around 2 and 3 o'clock, and minimum temperature around the 5 to 6 o'clock in the morning. Those temperatures will kind of increase continuously. And the sea level rises, I just mentioned, increasing ocean temperatures, more frequent and heavier floods because of global warming. And we expect development of super typhoons, or we already start to see that because of warmer sea surface temperature. On the other hand, we expect more severe drought and arid conditions over the world. Desertification, such as Mongolia area, is one aspect of those increasing drought, arid conditions in the world. And Arctic sea ice will disappear at some point. And all the mountain glacier recession and retreat will be seen, and probably will lose all of those mountain glaciers. Thawing permafrost is one dire consequences nowadays because in the cold temperature, people build houses and buildings or roads over the permafrost area. Now those permafrost now is getting melt away. So those ground will be collapsed, so giving a lot of damages to those constructions and infrastructures, the houses, you name it. So this is actually happening over the world. Other indirect factors also dire. We see more often the hunger and the water crisis, especially in developing countries. And our security is lost due to the floods and forest fires. Every year, we more often hear about wildfires and the flood from the globe. And health risks due to increasing frequency and intensity of heat extremes and extreme humidity. And we expect increasing spread of pests and pathogens. I think COVID-19 is one of those. I'm not sure about that, but certainly more discussion, I hope, in this webinar. And we'll expect a loss of biodiversity that is happening actually in the globe. Ocean acidification due to increased HCO3 concentrations in the water as a consequences of increasing carbon dioxide. Thus, all kind of adaptation in all areas may be needed. For example, agriculture, forestry, and other infrastructures and tourism as well. Okay, thank you very much for listening this talk. I appreciate your listening. Thank you.
Thank you, Professor Son, giving great presentation for global warming situation. If audience, you have any kind of comments or any question, please use and record the chat box on the webinar website. We will collect your comment and we'll discuss end of this section. Okay, next speaker. Okay. Next speaker is Professor Christian Fransk from Busan National University. He is an associate group leader at the Center for Climate Physics of Institute for Basic Science. His topic is climate change impact on global health. Would you please start your speaking?
Okay, welcome everyone. I first want to thank the organizers for inviting me and giving me the opportunity to talk here on this important topic. So my name is Christian Fransk. I'm from the Center for Climate Physics, Institute for Basic Science, and Busan National University. So I'm going to talk about climate change impact on global health. And thanks to Professor Sohn, we already have some introduction to global warming physics, why we have global warming, what we already experienced and what we might experience in the future. So I don't probably have to say too much about this here, but in this slide, first wanted to point out, as Professor Son already did, so here we have a reconstruction of the last 2,000 years of global mean surface temperature, which was relatively constant, but then we also had this decrease in temperature. But then with the start of the industrialization, once we humans started to emit CO2 due to the burning of fossil fuels, we had then this really unprecedented warming, which is, I think, by now 1.2, 1.3 degrees warmer than warmer than in pre-industrial times. And also important is to point out that's really the speed of the warming, which also makes it much harder for ourselves and ecosystems to actually adapt to this. And how do we know that this is really due to humans and not due to natural climate variability? So we can use climate models and basically then decide how we actually force them, whether we only use natural forcings like solar variations or volcanic eruptions, or if we also include human forcings like CO2 increases due to burning of fossil fuels. And if we basically do those different sets of climate model simulations, then we see here the black line, that's basically what we observed of the temperature changes over the last few decades. Then we basically see, unless we actually include human forcing, human or anthropogenic greenhouse gas increases. So that would be here the green line. If we don't include this only natural forcings, then basically we cannot explain what we observe. And in order to explain this, we basically have to include the human-caused greenhouse gas emissions. Then, so that's the past. So if we then also want to say something about the future, so we have to make certain assumptions how our emissions will evolve in the future. So that some of our colleagues basically have thought about this a long time and came up with those 5 different scenarios. Some which are very high emissions, say that would be like business as usual. Say if we wouldn't change our behavior, the amount of CO2 emissions we produce every year, or if we then really try to reduce them by going to renewable energies, for example. And by 2100, then we can expect different amounts of warming, somewhere between 1.5 and almost 5 degrees. So that's already very concerning. But if we now also look, what would be the impacts of this? And that's here in those amber plots, or we call them amber plots. So the colors basically indicated the risk. If it's very dark, then we have a very high risk or very large impacts. If it's white, basically we wouldn't see any impacts. And then yellow would be moderate. And then we can also see here different temperature levels, how the colors change. So we have here, the first would be unique and threatened systems. So that maybe some coral reefs might disappear, or disappearance of Arctic sea ice, extreme weather, that they become more frequent and intense, distribution of the impacts, whether they're more localized or if we feel them globally. Then also global aggregate impacts or large-scale singular events. So that would be if certain circulation systems, for example, the Indian monsoon would really change drastically, which then also would impact millions or even billions of people. Then we can look here at different temperature levels and then basically see how the color code here changes. And I always get often asked why we should limit global warming to 1.5 or 2 degrees of warming. Then we can basically see here, if we limit global warming to 1.5 degrees, then we can minimize the risk and the impacts of most of those effects here. If we go to warmer warming levels, 2 degrees or so, then the risk that something bad happens will increase. So we can also look into this into a little bit more detail. So in those amber plots show basically impacts and risks to terrestrial and freshwater ecosystems. So the biodiversity loss, if we would really go to 2 degrees warming, then there would be a relatively large change, or tree mortality also increases with increasing temperatures. Then wildfire increases. Of course, it's also related to higher temperature, and of course also drought conditions, less precipitation, and also carbon loss. So that's, of course, if we have biodiversity loss, they more desertification, so we have less plants, and plants actually take up carbon. That's also one of the major carbon sinks. And if we basically also lose this, then of course more carbon will be in the atmosphere. And there's already some indications that one of the major carbon sinks, the Amazon wild forest, basically, that might already transition to carbon source, so that instead of binding carbon, CO2 from the atmosphere, it actually would emit more and more CO2 in the future, which also makes it much harder to combat the climate change effects and to mitigate our emissions. And here we can also look at impacts and risks of ocean ecosystems. So we have warm water cores, so they're already threatened right now. Maybe in the news, you've seen those news about the Great Barrier Reefs in Australia, where basically those warm water cores, or nowadays almost every year, basically, it's called the so-called bleaching event. So basically they all lose their nice colors and become white, and there's also the threat that they might not recover in the future. And of course, there are lots of other ecosystem impacts there. So what I want to focus more on in my talk today is, of course, health impacts. And here we can also already see lots of health impacts. And if we go to larger temperature levels, they also will become more severe. But then we can also here distinguish whether we actually adapt or make some proactive adaptation measures, so that we already invest, say, in our healthcare systems, or say we would have limited adaptation, basically no adaptation, so we wouldn't really prepare for future health effects of global warming. That's, of course, and also changes basically the risk and impacts we face. So here for heat-related mortality, that's, of course, if we would already invest, then basically we could really manage the impacts. If we don't invest, then of course we would face very severe consequences. Then here also on related mortality, that's related to air quality. That's, of course, also of a major concern. Then malaria. So if we get to warmer and more humid conditions, then of course also mosquitoes can spread to new areas. So malaria actually could also spread to new areas. So, and that's of course also of concern, but also if we would invest into healthcare, that we could also manage this, or other infectious diseases like dengue fever and such things. That's of course also something we have to be prepared, because with warmer, more humid conditions, those mosquitoes which basically distribute those viruses can basically spread to new areas. Okay, heat wave exposure, to see how this actually has evolved over time. So when it comes to mortality, then it's especially young people, younger than 1 year, are affected, or elderly people who are older than 65 years. And here we basically see for a couple of different countries here, over the last 10, 15 years, we really see this drastic increase in the exposure. So that's basically the change in % days of heat wave exposure relative to this baseline. So we already see those very severe impacts. And if we also look at, say, the different countries and how well they are developed, or basically whether they're rich countries, that would be here the green line, or relatively poor countries. So that's meant here by HDI, Human Development Index. So you can basically see this as some kind of a wealth index, and here I show the activity loss. So heat wave exposure not only increases mortality of people, but also working age people might not really face a higher risk of dying, but they might lose labor or efficiency because it's hot, so we are becoming less efficient by working. But in rich countries, we of course mainly work indoors, so that's also something we can manage. So we have here in Korea air condition, but in poor countries where they typically work out in the outdoors, that's of course more of a problem because that's much harder to manage. I mean, you can maybe change the working hours when you work, maybe not during the hottest period of time, then maybe more in the very early morning or then more in the evening, but that's also only a limited flexibility of adapting to this. So that's of course always the discussion about the costs of global warming is always kind of focused to the future, but we already increased our spending on healthcare. So that's again here for different classes of HDI, Human Development Index, and the rich countries, we already increased our spending on the healthcare sector or health relevant sectors considerably, especially in relation to more poor countries. So that's of course also of concern. So that's especially in poor countries, increase in healthcare spending probably would have would go much further than in developed countries. But that's already some costs which we probably don't really factor in already in the damage or in the cost of global warming, which we already pay. Then here also the number of deaths we can actually already attribute to heat. That's for the year of 2019. That's for heat-related deaths of people older than 65 years. You can already see here a couple of countries where we had very large numbers, somewhere between 10,000, 100,000 heat wave-related fatalities in 2019. So I'm from Germany originally, so in 2019 we had a heat wave, and of course that also then increased the mortality that year. Also here in China and India, they also face or already experience very hot temperatures already. Then something related to what the symposium will be focused more tomorrow, infectious diseases. So we already see here also changes or increases here for dengue fever. Over the last couple of decades, we see some increase. Or here malaria, especially in poor countries, we see a considerable increase, whereas here in developed countries, it's relatively or very small, but that could also change because due to global warming, also malaria could actually return to developed countries. Even so, we might be better able to actually manage this because we have much better healthcare systems than developing countries. But that's also a point we should consider spending more money in developing countries on healthcare. Or then here, some other bacterial diseases where you can also see that they kind of increase over the last few years and decades. Then something which is not directly related to health impacts, but indirectly is of course food security. If we don't have enough to eat, or what we eat is not nutritious enough, that of course also then has impacts on our health. And what's plotted here is basically the length of the growing season, and we already see that's over the last few decades also decreased. So that's of course also of concern that we might have more problems with feeding people in all countries. So that's, yeah. Okay. As Professor Sohn also already mentioned, extreme events will become more frequent and more intense. And I now want to talk a little bit about that also, how much they actually increase, to say the fatalities, how many people actually die through this. So also here in Korea, we face typhoons like this one, and basically then we also have the storm surge, or we just have flooding events and heat waves. And I looked into a database where basically they recorded how many people died due to different extreme events like drought conditions, heat waves, flood conditions, or storms like typhoons over the last decades from 1960 to 2020, and that's data for the whole globe. And we can see here that actually drought conditions are basically the major cause of fatalities due to weather or climate extreme events. Heat waves also kind of very considerable flooding events, and of course storms. They also cause lots of fatalities. And what I want to point out here, so those light blue bars, that's basically the mean, so that would be the expected number of fatalities per year. And the dark blue, that would be the median. So, and you can see here, there's a very large difference between them. That already indicates that the distribution would be heavily skewed. So that means just a few events of those extremes cause the majority of the fatality. So that's looking at the mean number might not that informative. So because we might have here very severe events that you can also see here in this time series. So most years you don't really see many or large numbers of fatalities, but then there are individual years where we get huge amounts of fatalities. Then we can also look at different continents. If we just look at the total number of fatalities, then Asia is actually the continent which is or has to face the most severe consequences of fatalities to weather and climate extreme events. But if we actually would put this into relation of the whole population, since in Asia a huge number of people are living, so that's actually then already puts this more in relative to the other continents. So that's considering the population size, actually it's much more mixed picture which continent actually would be most affected. So that's more uniform for all the continents we considered here. But of course, just the total number is of course also of concern. So trying to adapt to weather and climate extreme events, or trying to adapt to global warming would also then lead to much better to reducing number of fatalities. Then we also looked at the trends, and you can see here in this schematic that on most continents we see at least certain extreme events which lead to increases in number of fatalities. So if we go here to Asia, then we see heat waves and flooding events lead to increases in fatalities, where storms and the overall number actually is going down. So that's of course, so that's might already indicate that that Asia already has started to adapt or can deal better with the impacts of climate change. Then I also did a statistical analysis. So I treated the number of fatalities as an extreme event. So there is the statistical theory of extreme value statistics, which you can use to actually look what's the probability is of a big event to occur in a given year. Or we can put this into something like a 10-year level event. So if we look at extreme events which would occur once every 10 years or 25 years or once every 50 years, so once in a 50-year event would be, of course, a very big event. Then we can basically also look here how many fatalities we can actually expect. And you can see here that, of course, those very big events then cause very large numbers of fatalities. Okay, that was more the direct impact of extreme events on the number of fatalities. Now we can also look at infectious disease outbreaks and whether this is they are related to climate change. So again, we looked at this database and looked up infectious disease outbreaks. They have a very large number of infectious diseases, like those dengue fever, Spanish flu, cholera outbreaks, and so. And then we also looked at COVID. So here the idea was to look how unprecedented this was compared to previous infectious disease outbreaks, or whether the magnitude was to be expected. And that's something we did last year. So we basically looked only at the data of 2020. And so, but if we would continue or also look at last year's data, that of course probably would affect our results a little bit, but I think the major conclusions would still hold. And here you can see, compared, say, with the Spanish flu, if we look at deaths per 100,000 people, so it's actually not that unprecedented, but of course, for many decades, we only had here very minor infectious disease outbreaks, or infectious disease outbreaks which didn't cause that many deaths. Then we can also look here at different continents, and we can see here that Asia actually fared relatively well, especially North America, South America. They fared very, very badly compared with previous infectious disease outbreaks. Then that's probably a very technical slide to just show you some numbers. Here, basically, we looked at the probability, whether we only use data before COVID or without COVID-19 fatality numbers, or then also included them. And what we found, basically, probabilistic speaking, we don't really see a difference. So the probability of the number of deaths or fatalities due to COVID-19 in a way was to be expected. So it's not really something, at least if we look at past data, which was unprecedented. And here we can also look at the return levels, and you can also see for different continents, they vary quite considerably, but also that's including COVID-19 data actually didn't change them that much. So what's also interesting is whether there is an impact of climate. So we can basically extend our extreme major statistical model to include some climate indices. So we can compute this without any climate impacts. Then we can use here global mean surface temperature and index for ENSO, which is of course also very important in the climate system, the Atlantic multi-decadal oscillation or the Pacific decadal oscillation, two important ocean climate indices. And we also considered some generic trend functions, so to also try to account for effects outside of the climate system. And we can see here this bold number for South America. That's the only significant impact of a climate indices we can find. So that's here the Atlantic multi-decadal oscillation. That's basically how the sea surface temperature, the temperature of the Atlantic Ocean changes, and that changes on a very slow time scale, as you can see here on decadal time scales. And for most of the continents and also worldwide, we basically see this trend function as the most important factor in affecting the probabilities. So here I displayed the global mean surface temperature, where we of course see the increase, and here our linear trend function, which we also consider. And one possible explanation for this is, of course, also some human impact, but not directly related to global warming. It's basically that due to the population spread of humans, that we move more and more into wildlife area, so we get more into contact with wild animals. So what's displayed here is basically color coded. If it's dark green, that's the wild area, so basically almost no human influence. And if it's already very dark red, that's basically there's of course humans already changed the ecosystems considerably. So and that's of course also areas where we already came into contact with wild animals, probably domesticated them, but there's of course still some areas where we have wildlife, and say bats, they can carry lots of different viruses, and they might then jump onto humans, but that's a topic for tomorrow's webinar. Then maybe in the end, I just wanted to also discuss a bit the complexity of what we might face in the future, so-called cascading hazards from climate to society. So if we just focus here on the Indian subcontinent, Himalayan, here we of course see a considerable warming already. So as also Professor Son already mentioned, that this increased warming will lead that glaciers will melt. So this high altitude warming, so we have more snow and glacier melting, which then also increases river runoff. And if we then combine this with more extreme precipitation, that's here, say, for India, where we looked at 2 different years, 1989, where we have the distribution of precipitation intensities, and then with 2100, and here we can see that much higher rainfall amounts per day will be much more likely by 2100. So, and now we can basically see if we have increased river runoff due to snow and glacier melting here in the mountains, if this will be then combined with more extreme downpours, so we can have loss of infrastructure that can also affect crops agriculture, but of course also health impacts. So if we also then focus here on the Indian subcontinent, there's of course flood-related diseases such as malaria, dengue, diarrhea. And if we look at future conditions, say this 8.5 scenario, very strong warming, then we of course also the risks increase of those cascading hazards, so that we have those flooding conditions, and then they might actually lead to infectious disease outbreaks. That also the areas where this is a very high risk also then increases with warmer temperatures. Then another thing would be food security. We have multiple bread baskets here over the US, Western Europe, Eastern Europe, and also here China. And there's of course also this threat that due to changes in the atmospheric circulation, we might actually have simultaneous drought conditions over multiple of those bread baskets. So that's of course also some work going on which show that's a possibility. And if we just look at the current situation, one of the major corn producers is Ukraine. So we have the war currently going on. That of course will also affect the corn yield. So that's already leads to increases in food prices. And you can just imagine maybe we might have drought conditions in the US or Western Europe. So that might then actually pile on those problems we have to face. Here we also looked at some of those interactions, since we think those cascading effects between the natural Earth system and the human Earth system should be much better modeled, included in our model. So we have here different systems, Indian monsoon, which can basically change or would then have impacts on, say, extreme climate events, food security, which then might have lead to cascading effects into socioeconomic impacts like human health. Then, of course, social responses, which then might affect our willingness or unwillingness, our ability or inability to actually try to mitigate climate change emissions. So here my summary. So I showed some slides that anthropogenic global warming is unequivocal, so that it's really clear that we humans cause it. Extreme weather and climate events already occur more frequently and are more intense, and they also will become more frequent and more intense with future warming. And that also leads already to widespread damages, losses to ecosystems, our economy, and human health. And with increased warming, that will only get worse. And then we already see that the number of fatalities to extreme events has increased, and also evidence that infectious disease outbreaks have increased. Not necessarily due to global warming, but due to human population spread pressures. And also those impacts and risk of extremes or global warming become much more complex. Thank you very much for your attention.
Thank you, Professor Fransk. It was an impressive presentation for climate change issues, especially connected with infectious disease. The audience can use a chat box for your comment or any kind of question too. We move to the last presentation. The last speaker is Professor Junseok Choi from Seoul National University. His topic is tick-borne zoonotic severe fever with thrombocytopenia syndrome. We call the SFTS. The presentation we are going to be a video presentation.
Hello, everyone. My name is Junseok Choi. I am a professor working in College of Veterinary Medicine at Seoul National University. I am grateful for the opportunity to present my research at the Harliman International Symposium. Today, I would like to talk about the overview of tick-borne zoonotic severe fever with thrombocytopenia syndrome related to climate change. My presentation will include the introduction, a brief description of SFTS virus in ticks and animals, transmission and conclusions. Ticks are the oldest surviving animal species on the planet, transmitting a variety of zoonotic pathogens to humans and animals. Recently, it has been known as a vector of the virus that causes severe fever with thrombocytopenia syndrome, a disease with a very high fatality rate in Asia. Global warming due to climate change can improve the tick habitat in Korea. And it is predicted that ticks will continue to pose threat of disease to humans and animals in the future. Two studies have reported that the distribution of ticks and the spread of related disease due to global warming are increasing. In this slide, you can see the spread of ticks and tick-borne Lyme disease in North America and Northern Europe. The authors believe that this cause is related to climate change. There was another paper that reviewed the investigation of tick-borne disease for the past 10 years in Slovakia, one of the European countries. The authors explained that the increasing trend of this tick-borne disease is related to global change as well as advanced in disease diagnosis technology. As you can see, these researchers spread of tick-borne disease is increased by climate change. This slide shows how climate change spread zoonotic disease like tick-borne disease. This is an infographic of the diagnosis, dangerous cycle that climate change creates for zoonotic disease. Humans expand the wildlife-urban interface, and climate change increase homogenized habitats, creating areas of increased biodiversity where novel species interactions can occur. These interactions present an increased risk for the spread of zoonotic disease. Environmental change due to climate change are increasing the density of wild animals and ticks in Korea. National Institute of Meteorological Research in Korea reported that Korea climate is expected to change to subtropical zone until 2100, excluding high mountain areas. Recently, the density of wild animals and ticks vectors has increased due to nature conservation and animal protection activity in Korea. In addition, in relation to the increase of outdoor activity of people, the possibility of contact with the vectors has increased. Therefore, it is predicted that infectious disease will likely to increase. There are many factors of disease transmission, especially life cycle, food chain, vectors, reservoirs, and migratory birds. Migratory birds bring along ticks and pathogens and passes over the borders to other countries. Recently, it has been reported that the transmission of SFTS virus may be related to migratory birds flyway in Asia. Therefore, we need more detailed study on the relationship between migratory birds, ticks, and SFTS virus. Korea is an important stopover land for migratory birds. Korea is the middle of East Asia, Australian flyway, which is a stopover site for migratory birds. There are researchers going on in Korea to investigate the spread of SFTS virus by ticks on migratory birds. Borson Center in Korea, National Park Research Institute, collected ticks when catching birds for the banding program. We discovered several new species of ticks collected from migratory birds that have not been reported in Korea, and several pathogens, Anaplasma and Borrelia species were also detected. Therefore, we will be able to establish preventive measures based on the study on the interaction between migratory birds, ticks, and SFTS virus in East Asian flyway region. Now I will talk about SFTS virus. Severe fever with thrombocytopenia syndrome virus is a group 5 negative single-strand RNA virus. This virus species was finally named Tabibanda virus. The virus has 3 segments, L, M, and S. And the virus genome size is 11,490 base pair. It is very small size virus. SFTS virus is newly recognized hemorrhagic fever disease found throughout East Asia, China, Japan, and Korea. The SFTS is an emerging infectious disease first discovered in China in 2009. In 2011, The first human infection with SFTS virus was officially reported in Western China and then reported from Japan and Korea in 2013. Recently, the SFTS virus detection area has been continuously expanded in Asian countries. SFTS virus transmission to human commonly occur from virus carrying tick bite. The SFTS virus then invades the lymph node, targeting immune cells such as B cells, impairing host immune response from invading pathogens. SFTS virus causes system circulation, viremia, cytokine storm, and severe inflammatory response syndrome after further replication. Thrombocytopenia is a hallmark of SFTS virus infection. Disseminated intravascular coagulation and endothelial damage caused by cytokine storm lead to multi-organ dysfunction, reflected by the elevation of liver, kidney, and heart serum markers. SFTS virus infected person have a severe fever, leukopenia, thrombocytopenia, and elevated liver function values. If doctors did not earlier diagnosis, patients may have this multifunction organ failure and die. Currently, the genotype of SFTS virus classified into 6 genogroups from genotypes A to F. And genotype B is divided into subgenotypes B1, B2, and B3. In Korea, the genotype B is the most common, accounting for about 77% in humans and 68% in animals. All genotypes of human SFTS virus have been found in Korea, but only genotypes P, T, and F have been found in animals so far. The genotype A and F of the SFTS virus showed low virulence in mouse infection studies. Therefore, we need a specific study on the virulence according to the genotype of SFTS virus. This slide is the geographic distribution of SFTS virus. The genotype of SFTS virus in China and Japan are different from each others. And both the Chinese and Japanese genotypes are found in Korea also. In 2020, my lab first discovered a new subgenotype P4 of SFTS virus in cats and cows. These findings suggest that this SFTS virus has genotype that has not yet been transmitted from ticks to human or animals to human. Or it is thought that we need to do more research to find out whether a genetic mutation or SFTS virus in host animal is the cause. Last year, 2021, one of the SFTS human patient in 군위군 경상북도 therefore, Korea Disease Control and Prevention Agency tried to multi-ministerial joint surveillance with National Wildlife Disease Control Center. NWDCC collected blood samples and detected ticks from captured Korean water deer in same area of SFTS patient in 군위군. We tried to test for SFTS virus, and we got PCR positive from Korean water deer and ticks also. We analyzed the sequence of the SFTS virus, the genotypes of S segment was of genotype B4. The genotype were identical SFTS virus among human patient, Korean water deer, and ticks. This result showed the transmission life cycle of SFTS virus in the nature, in ticks and animals, and then transmitted to human in same area. The ecological habitats of Korean water deer and active while inhabiting within 150 meters from the human living village in rural areas. In this surveillance, we need to better understand the natural ecosystem and approach disease prevention. This case was the result of cooperation of each department based on the One Health concept. In Korea, sepsis virus was first isolated from human patient in 2013. The number of sepsis infection cases has been steadily increased during 5 years, and then a little bit decreased in Korea. Since 2013, total 1,512 people have been infected with the sepsis virus, and 278 people died. The case fatality rate was 18.4% in human. It was higher than any other infectious disease. Our laboratory has been conducting research on sepsis virus in ticks and animals since 2013. Ticks were collected from natural environments and animals, and sepsis virus was detected by collecting ticks and blood samples from companion, farm, and wild animals. Main dominant tick species in Korea is Hampshire longicornis, more than 95% than Hampshire flava, Ixodes niponensis, and Embryoma tetradinaridium. Ixodes ovata is very rare species. We collected only 1 ticks in Togisan National Park in Korea. We collected also 4 different tick species from wild boars, especially Embryoma tetradinaridium is a host-specific tick species that blood sucks in wild boars, snakes, and humans. In our study, for detection of sepsis virus antigen from ticks and animal samples, nested and real-time PCR and nucleotide sequence analysis were performed. And also, we established the IFA and ELISA method for antibody investigation against the sepsis virus. We surveyed for sepsis virus in 5 national parks in 2015, 북한산, 치악산, 우대산, 덕유산, and 월출산 National Park. We collected the ticks on trail and non-trail of the 5 national parks, and then compared the number of collected ticks and infection rates of sepsis virus in ticks. There was no statistical significance difference in the number of collected ticks and detection rates of sepsis virus infected ticks between trail and non-trail. This result means that while the animals do not move to trails during the daytime, however, at nighttime, when there are no people, wild animals also spend a lot of time moving or staying along the trail. Therefore, ticks are also collected on trails. Here we have the result of the detection of sepsis virus in ticks collected from 5 national parks. Infection rate of sepsis virus in Hampshire longicornis adult and nymph is total 4.77%. Total infection rate in all of the ticks was 3.67%. We searched for sepsis virus from ticks on Gwanaksan and the Seoul National University campus in Seoul, Korea. Gwanaksan is one of the mountains in Seoul. Many people enjoy hiking on this mountain. We did not find any ticks from SNU campus, but we collected 273 ticks from Gwanaksan and tested for sepsis virus infection. We collected 2 different kinds of tick species, Hampshire longicornis and Hampshire flava. Infection rates of other and NIM was 3.2%, and LABA was 2.3% as MFIR. Our research was conducted to detect the West virus in ticks collected from Korean water deer and wild boars. Total infection rate was 4.98%. This result was similar to the detection rate of SFTS virus in ticks collected from humans. Now I will talk about the detection of SFTS virus from domestic, wild, and companion animals. First, we collected blood samples from domestic pigs for detection of SFTS virus in 2013. Pigs were bred in a traditional way near the mountains. We collected 240 blood samples of domestic pigs from 8 provinces and detected 4 SFTS virus infected pigs. Total detection rate was 1.67%. This table shows infection rates of SFTS virus from 268 black goats in 4 different grazing ranches. 14 black goats from 3 farms. SFTS virus antigen was detected by PCR in 14 black goats with detection rate of 5.2%. We investigated SFTS virus infection in wild boars. The total average detection rate of SFTS virus was 4.3%, and the total average antibody positivity rate was 28.8%. We also detected the antigen and antibody of SFTS virus from poultry, chicken, ducks, and wild geese. The wild geese were collected from farm-raised animals. Total detection rate of SFTS virus from poultry was 2.5%, and total seropositive rate is 30.3% by ELISA. As a result of sequence analysis, subgenotypes B2 and B3 and the genotype D were found from poultry SFTS virus. We tried to detect the SFTS virus from stray cats. Total infection rate was 17.5% in Seoul. We did a study to detect the SFTS virus from Korean military dog. The training environments of military dogs is highly exposed to arthropod vectors. 3 sera out of 103 dogs showed 2.9% positive for SFTS virus and isolated virus also. We tried to detect the SFTS virus from horses from Innan and Jeju Island. Total detection rate of SFTS virus antigen was 2.1% in Jeju Island only. And total positive rates of antibody against SFTS virus were 24.2% in Innan and 33.7% in Jeju Island. We conducted a study about clinical and epidemiological characteristics of the patients with SFTS in companion animals. This slide shows one of the clinical cases about SFTS virus infected dog patient. The patient was a companion dog living at an apartment at Chungju City in Korea. He was admitted into a local animal clinic with fever and anorexia. Before visiting the animal hospital, he often walked in the grass near Tanggeumdae Park in Chungju City. The scab tick bite was discovered in the region around his left armpit by the dog groomer. And subsequently, he developed fever and anorexia. Based on this patient clinical symptoms, blood test, antigen and antibody test, the final SFTS was confirmed. and the virus was also isolated. In this research, we surveyed the SFTS patient dog and cats from 166 small animal clinics in nationwide. We found 14 dog patients with SFTS clinical symptoms out of 448 dogs. And for SFTS virus positive out of 112 cats in 2018 and 2019. Many of SFTS dog patients shows clinical symptoms: anorexia, depression, vomiting, and diarrhea. Leukopenia, thrombocytopenia, elevated value of CRP and the liver function test. We got subgenotype P1, P2, and P3, and genotype T from dogs. This is confirmed case of SFTS in companion cats. SFTS virus antigen was detected in 4 out of 22 clinical cases of cats, and 1 cat died. Clinical symptoms in cats such as anorexia, jaundice, thrombocytopenia, leukopenia, and hyperbilirubinemia were detected. Jaundice cat was seen in most patients with SFTS infection. From 2018 to 2020, we detected the SFTS virus from companion, farm, and wild animals. We detected SFTS virus antigen or antibodies from a total of 14 animal species. The average detection rate of SFTS virus in all tested animals was 2.4%, and antibody positivity rate was 20.5%. Most of animal species a higher positive rate of antibodies except cat and goat. Cat is a high mortality rate in Japan. Therefore, positive rate of antibodies is low. We collected goat blood from slaughterhouse, and recently the goat were rearing in barn. Therefore, goat less chance to contact ticks. In this map, SFTS virus infected animals were identified all over Korea, and Gyeonggi, Gyeongbuk, Jeonnam, and Jeju provinces in particular showed high antibody positive rate. This studies the pathogenicity and the potential for intraspecies transmission in experimental infection dogs with SFTS virus. Secondary transmission by contact has been demonstrated when healthy dogs are co-housed with infected beagle dogs. This slide is a photo of a veterinarian at a veterinary hospital in Gyeonggi-do, presenting his experience in 2019. While treating a dog who had been bitten by ticks and had severe clinical symptoms, blood deficits and hematemesis, thrombocytopenia, and abnormal values of blood test, and the dog patient died. The dog patient died within 2 hours. The veterinarian showed severe clinical symptoms after 10 days and was admitted to the intensive care unit of the university hospital and was diagnosed with SFTS virus infection. It is strongly presumed that veterinarian who treated the patient was infected with secondary infection through cross contact with the infected dog. This slide is a summarized schematic diagram for based on the study of the transmission cycle of SFTS virus in nature. The ticks are competent vectors to transmit the SFTS virus in both transovarial and transstadial transmission mode. The SFTS virus primarily impacted humans and animals through ticks. Secondary infections have been confirmed in human-to-human transmission of SFTS virus. But there is still no scientific evidence of secondary infections between homologous or heterologous animals or animal to human. But recently, experimental animal species transmitted to same species of experimental ferret and beagle dog model. Also, recently, one of the veterinarian infected with SFTS virus from hospitalized cats. This is a secondary infection case from animal to human in Japan. Also, total 16 persons infected with SFTS virus from dogs and cats, and one veterinarian and one guardian died in Japan. This is a very important issue of the public health. The government should establish guidelines for the infection of the animal SFTS virus to ensure that there are no secondary infections of animal workers or guardians. Currently, there is no commercialized therapeutics or preventive vaccines, and R&D are in progress. Since SFTS is a very high fatality rate in humans, therefore the government must make large-scale investments for rapid basic research and clinical trials to develop vaccines and therapeutics. Human and animal medical staff should wear personal protective equipment to prevent secondary infection when treating patients with suspected SFTS. There has never been a complete eradication of ticks and tick-borne disease after they were identified. So how should we control ticks and tick-borne disease? A lot of research has been done to solve this problem for a long time, but a complete tick control program has not yet been developed. Therefore, this issue should be solved based on one world, one health concept according to the climate change. In order to protect humans and animals from SFTS virus and numerous tick-borne disease, rapid diagnosis, treatment, and vaccine development of disease are required. In addition, fundamental and continuous basic research and development is needed to eradicate tick vectors. These are funding sources for the SFTS research in ticks and animals. Thank you very much to all of the research members. Thank you for your attention.
Speaker.
Thank you for the good presentation for Professor Che. Before panel discussion, Professor Yu-Hwan Kim, he is previous president of AASSA, will give a brief comment. Professor Park will introduce him.
Okay, before we move on to the panel discussion, I'd like to invite Professor Kim Yu-Hwan, who actually initiated this wonderful webinar in the beginning. He is the former president of AASSA. Please welcome to Professor Kim. His greetings for this webinar. Please.
Thank you for a kind introduction. I'd like to introduce to you what is AASSA and what is IAP first. We have, as an international association of the national science academies and also the medical academies. We have inter-academic partnership, which is a global association, which comprises of more than 140 national science and also the medical academies, kind of United Nations in scientific field. Under the IAP's umbrella, we have 4 regional affiliates representing the continents. In Europe, we have ESAC, European Science Advisory Council, and in the North and the Caribbean areas and North America and the Caribbean and also the South America, we have IANAS. And also for representing Africa, we have NASA. And for this region, Asia and the Pacific, including Australia and New Zealand, we have AASSA, okay? Association of Academies and Societies of Sciences in Asia. The AASSA usually hosts about 4 to 6 workshops or conferences or symposia every year. But due to the COVID-19 phenomena, we are forced to hold these meetings in virtual spaces using the Zoom meetings like this. I as immediate past president of the AASSA, would like to thank all the speakers for excellent talks today. But I have one question to ask to you, okay? In addition to the melting of iceberg, we have confronted with the thawing of permafrost in Siberia, okay? Which I think that thawing of the permafrost will have profound effect on the human activities and also on the release of pathogens. For example, we either open the northern sea passage from the maritime transportation from Asia to Europe, either increased human and nature contact, and also thawing of the permafrost in Siberia will open the human habitat quite widely too. So we, the scientists in the world, are concerned about the release of the pathogens which have been locked in the ice until today, and also we are faced with new pathogens which are unknown to humanity until today. Maybe I'm afraid. Do you have some comment on this problem?
Well, thank you, Professor Kim, for the great foundation history of AASSA. Now we are going to panel discussion for this section. Unfortunately, Dr. Che is not attended in this conference room today, so we'll have a conversation without him. First of all, would you please give any comment or a question for today's speaking on the floor? Okay.
Yes, I think I may be not the right person, but I brought the thawing permafrost issue today because the warming due to carbon dioxide emission is very pronounced in high latitudes. I showed you today where the highest warming actually takes place and will take place in the future. That is the high latitude, including Siberia and probably northern North America and the polar regions. So the question, if I understand, is that throwing the permafrost area is giving a lot of issues, actually, not just new release of pathogens, which I don't really honestly know about that, but that is unknown area to all of us, not just to climate sciences, but as well as to this zoonotic infectious disease, because everything got frozen for thousands and thousands and years, all just buried there, covered with ice and snow. And it was very recent to discover old carcasses of dead bodies, and all the area got swamped, and all infrastructures are getting melted away, and the roads are just broken down into kind of rough roadways, and the houses got demolished. We observe everything, and even there are more carbon dioxide emission because of the debris from previous forests and vegetables. They all stayed there, stored there thousands and thousands of years. Now we started to see those things coming out. Why not the pathogens stored in associated with animals and forest remnants and vegetables, or I mean the biomasses? So we see more and more often see those results coming in the future. And probably your infectious disease scholars and researchers pay more attention to those new coming issues. I believe there will be certain issues coming very soon in those areas.
Okay. Is there any kind of...
Can I add something
okay.
to this?
Yeah.
I mean, another problem with permafrost thawing is, of course, in the ground there's also frozen methane. It's a very powerful greenhouse gas, and once it melts more and more, then also this methane gets released. So that will then also amplify global warming, so that we might actually have a positive feedback loop, that then the thawing will also accelerate more release of the methane, and of course whatever is buried there for thousands of years, potentially some pathogens, bacteria, viruses, would then also be released. So that's, of course, we don't know whether how threatened they or damaging they would be, or compatible they actually would be with modern humans. But of course, that's something we probably have to be a little bit concerned about.
Okay, thank you. Is there any other comment or question on floor? Okay.
I really appreciate this webinar, very valuable and fruitful. I really agreed with the Professor Kim Yu-hwang's comments. Those kind of phenomenon, for example, that avian influenza virus actually from the Siberia and Baikal Lake, long time frozen. However, the climate change released those virus from those area to come to that southern part of continent through the migratory bird. So as Professor Son and Professor Fransk mentioned about, those possibility is quite high risk induced through that kinds of phenomenon, actually from the climate change. I have one question to the Professor Fransk. You talk about that the presented about sleeping sickness, high death total on the year of 1900. How do you describe the ecosystem or climate change influence to these kind of sleeping sickness, especially outbreaks?
I mean, that was, of course, in 1901 or 2. That's, of course, long time ago. So by now, we might actually medically be able to treat this. I mean, that was the outbreak in Central Africa, which had back then a very high numbers of fatalities. If you ask me how large the risk would be of this happening again today, that's a little bit outside of my area of expertise. But since we haven't had really many outbreaks since then, that probably indicates that medically we are able to deal with this particular disease nowadays.
Okay. I'm not able to another question or comment on chat box. So okay, we are closed this symposium today. We are appreciated everyone you joined to this symposium. Thank you very much.